Do your thoughts ever come in order or are they a little bit more chaotic? Well, if your answer is the latter, then you already have an intuition for diffusion-based large language models. While mainstream LLMs like GPT predict text one token at a time, diffusion models take a very different approach. They produce an entire draft of the response and then improve it progressively. This is the technology behind models like Gemini Diffusion from Google, Mercury Coder from Inception Labs, and Seed Diffusion from ByteDance. The promise is phenomenal inference speed. These models are inspired by physical diffusion, the same process that describes how ink moves in water, which I covered previously. In this video, we'll focus on how such a continuous physical process can translate to the discrete world of language tokens. The mapping is really not intuitive at first, so if you want to build an intuition, then stick around. Today, state-of-the-art LLMs predict one token at a time based on the previously generated tokens. The result is left-to-right generation, similar to how we write English words on paper. This is the family of auto-regressive models, or ARMs. Diffusion proposes a new paradigm. A diffusion model generates the entire text sequence at once, starting with complete gibberish at time 0. At each point in time, it recomputes a full draft of the sequence. Some words persist, and some get replaced with better guesses. This refinement repeats over several steps, like a student revising an essay. Now, I want to point out a flaw in this terminology. While the next token prediction models are singled out as auto-regressive, I would argue that diffusion models are auto-regressive too, because they ingest their own output. They just differ in the granularity of the output, an entire response candidate instead of a single token. But I'll stick to the established terminology to avoid confusion. In image and video, diffusion models were clearly better than their predecessors. They brought generation to a whole new level of quality. But in language, auto-regressive models are already massively successful, so why are we even bothering with text diffusion? Well, in my opinion, it's because we can. The most honest reason is just intellectual curiosity. And this is an established pattern between natural language processing and computer vision borrowing ideas from each other. And some transfers are successful, like language transformers being successfully deployed in vision, and some of them are not, like convolutional neural networks, which started off in vision, never really took off in language. The jury is still out on text diffusion, but it does come with some intriguing promises. One promise is faster inference. This is particularly relevant for latency-sensitive applications like coding, but also convenient for LLM providers because a 10x speedup means 10x cost savings. ARMs perform one iteration per output token until the special end-of-sequence token is produced. Depending on your prompt, that can be in the thousands or more. Diffusion models can be faster because they require fewer refinement operations. The exact number is a hyperparameter that acts as a knob between speed and quality. For good outputs, a reasonable number of refinements today is in the tens or low hundreds. But new research keeps bringing this number down. Now, this reduction in the number of iterations is only meaningful as long as we can generate all diffusion tokens in parallel. Inception Labs report they built their own proprietary inference engine to maximize GPU utilization and ensure high token parallelization. And their efforts are paying off. A recent study from ByteDance, which is TikTok's parent company, shows that diffusion LLMs achieve speeds between 1,000 to 2,000 tokens per second on an age 20 GPU, while a comparable auto-regressive model will cap somewhere around 200. That's a 10x speedup already. Diffusion LLMs also promise higher quality outputs. The inherent left-to-right bias in autoregression limits the behavior of the model in several ways. An obvious one is, once a token is produced, it can't be revised. In this example, I asked the GPT-4o model a yes or no question. its response contradicted itself, going from a yes to a no after some intermediate thinking. But diffusion could have handled this change of heart more naturally by iteratively revising the entire response. Left-right generation can also lead to exposure bias or sampling drift. The model is trained to predict the next token for a ground truth prefix from the training set. But during inference, it has to complete its own previous output. So a small error can snowball as text gets longer, leading to drift. Currently, ARMs mitigate this with hacks like temperature or nucleus sampling. But diffusion would avoid this altogether by working on the entire sequence holistically. Finally, diffusion offers flexible prompting. While auto-regressive models expect the prompt to be a prefix, diffusion LLMs allow the prompt to sit at any arbitrary position. This addresses certain use cases more naturally. For instance, filling in missing spans in a PDF, rewriting a paragraph in the middle of an essay, or refactoring a block of code. ARMs can also do this already, but more awkwardly, often by regenerating parts of the document that shouldn't be touched. I suspect that AI coding tools like Cursor currently need a lot of special logic to incorporate the LLM output back into the existing code in the right place. So diffusion LLMs make interesting promises, but to me what's even more interesting is their implementation. These models are inspired by physical diffusion, the natural tendency of particles to disperse in the environment, which is inherently a continuous process. So in the image world, where pixel intensities are also continuous, it's a little bit more intuitive how we would apply it. But language is a very different beast. It's made up of tokens, which are not only discrete, but there seems to be no natural ordering among them. And since there's no single obvious answer, researchers proposed multiple implementations, which we'll discuss soon. But first, let's talk about the conceptual environment where diffusion models operate, the virtual space of motion. You can think of data as a landscape shaped by probability. In the visual world, hills are clean images that are meaningful to the human eye. These are high probability regions. And valleys represent pure noise, like the TV static. These are regions with almost zero probability. Largely, the same metaphor applies to the language domain. Well-formed text sequences sit on high probability hills and valleys are full of gibberish. But since language is discrete, the obvious question is, what do the two data axes represent here? Which brings us to diffusion in latent embedding space. Both images and text can be encoded into n-dimensional real-valued vectors called latents. They capture semantics without using pixels or tokens. You can think of their first two dimensions, x0 and x1, as the data axes in our landscape. Of course, in practice, the landscape has n dimensions, but we can't visualize all of them in a 3D plot. In this worldview, the process of generating data is similar to a particle starting from a noisy valley and climbing uphill towards real images or text. But the challenge is, at the start of the journey, the probability landscape is completely flat and there's no gradient to climb. One way to address this problem is to artificially spread out the hills so that the particle sits on a slope. As the particle progresses, we can gradually restore the true shape of the landscape. This dynamic terrain is basically a time-variant probability distribution P index T of x. This quantity is what we're trying to learn, and diffusion models simulate it using a cluster of diffusing particles. More exactly, simulating particles that diffuse away from real images is a way of producing training data. This process is called forward diffusion or noising. That's because a forward path takes the particle from real data to noise. When diffusion happens in latent space, we're not perturbing raw pixels or tokens directly, but rather embeddings. And during inference, we do the opposite. Starting from a noisy latent, we clean it up. This process is called reverse diffusion and is equivalent to moving the particle uphill. And finally, A decoder will translate the denoise latent back into the original space, be it pixels or tokens. For images, this is often a VAE decoder, where VAE stands for Variational Autoencoder. This can be a pre-trained, off-the-shelf model, potentially borrowed from previous work that had nothing to do with diffusion. High level, it consists of convolutions and upsampling layers that turn the n-dimensional latent into a two-dimensional matrix of pixels. Now here's the irony. For text, the decoder has to be autoregressive, generating tokens left to right conditioned on the latent. So what we have here is a hybrid model that leverages both diffusion and autoregression. This recipe is perfectly valid. Multiple papers do exactly this. But while this hybrid approach might fulfill some of the quality improvements promised by diffusion, the left-to-right decoder carries over some of the shortcomings as well. Which brings us to an alternative approach, diffusion in token embedding space. Instead of having a single compressed latent for the entire sequence, we could keep token embeddings separate and apply forward diffusion to each one independently. Effectively, we're preserving the token boundaries and removing the need for an autoregressive decoder. During inference, we'll similarly apply reverse diffusion to each noised token embedding. But here's where things get tricky. The denoised embeddings need to be mapped back to text tokens. This process, called rounding, turns out to be non-trivial. You see, the embeddings of our vocabulary tokens live in a vast continuous space. The denoised token embedding doesn't precisely correspond to any of these vocabulary tokens. The best we can do is choose the nearest neighbor, but given the sparsity of the space, the neighbor could be a completely arbitrary token. The difficulty of rounding is the reason why diffusion in token embedding space never really took off. Instead, state-of-the-art models converge to a solution that might sound unintuitive at first. They diffuse text tokens directly, circumventing any numerical representations. In our landscape, the data axes are now hosting the vocabulary. Every tick corresponds to a token. Note that there's no natural ordering among the tokens. Even alphabetical sorting is arbitrary from a semantic point of view. This 2D plane encodes all possible text sequences of length 2. In practice, we'd have hundreds of thousands or millions of dimensions, one for each position in the context window. In that huge hyperplane, there's one discrete point for every possible natural language text. Given the discrete nature of this space, the probability landscape is no longer a smooth mesh. It's more of a spiky terrain. We still see hill shapes with some sort of slope across the spikes. At first, the existence of such patterns might be unintuitive, given that tokens are naturally unordered. But in the hyperplane, two neighboring texts differ in only one token, which means the landscape does have some notion of locality. Just like in a continuous space, data generation can be viewed as a particle navigating the terrain in search of high peaks representing real data. In the previous video, we modeled the movement of the particle through the continuous image space using differential equations. But here, the particle doesn't follow a smooth path anymore. It's a chain of pops between discrete states, so we need a new mathematical framework. And that framework is known as Markov chains. Andrei Markov was a Russian mathematician who pioneered the study of stochastic processes. He lived in the same era as Albert Einstein and Norbert Wiener, who were building the theoretical framework for diffusion. We'll use Markov chains to model both the forward and reverse diffusion processes. Let's start with the forward process. At this stage, the true probability P of the landscape is unknown. All we have is a set of well-formed texts, and we'll use them to simulate training paths. This time, diffusion looked like dropping marbles from the vicinity of real data. Looking at a single particle, a Markov chain describes its movement from state to state, and we'll use a random variable x index t for each position in the chain. Just a quick heads up, I know we used x0 and x1 as axes earlier, but from this point on, xt will mean state at time t in the diffusion process. Same symbol, but completely different meaning. In a general probabilistic model, transitions are governed by some conditional probabilities q, where state xt depends on the entire sequence of past states. But in a Markov chain, this dependency reduces to just the previous state xt minus 1. That's the Markov property. This means we can fully describe the dynamics at each step using a transition matrix, which we'll call qt. The fact that q is time-dependent honors the time-invariant aspect of our probability distribution, just like in the continuous space. Each entry ij is the probability that the system moves at time t from state I, say this text, to some state j, say this other text. But here's the problem. The size of this transition matrix is effectively the number of all possible natural language texts squared, completely intractable. To work around this, we can make a simplifying assumption. Tokens are corrupted independently of each other. This is similar to image diffusion, where each pixel is noised independently. As a result, instead of one massive matrix for the full sequence, we just need a transition matrix over individual tokens, which has the size of the vocabulary squared. Much smaller than before, but still large. A vocabulary of 100,000 tokens would mean Q has 10 billion entries. One of the earliest solutions came from the D3PM paper, which tackled this by building character-level diffusion models. Since the character vocabulary is only a few hundred symbols, the full Q matrix could be stored and used directly. In one experiment, D3PM defined each entry Qij using the similarity between characters I and j in the embedding space. But modeling language at the character level proved to be a bottleneck in quality, so this approach never really took off. Another way to handle large transition matrices is to avoid expressing them at all, and instead define a closed-form rule for corruption. Here's a simple one, also from D3PM. This says a token will remain unchanged with probability 1 minus beta t, and otherwise be replaced with a random token drawn uniformly from the vocabulary. In this formulation, pure noise looks like gibberish. But many modern diffusion-based LLMs use a slightly different approach, based on a special mask token. This means a token will either stay the same or get replaced by a mask. There's no direct transition from dog to cat, just from dog to mask. So in this setup, pure noise is a fully masked out sequence. Now, you might remember from the previous video that beta t controls the noise schedule. When beta is 0, all tokens stay unchanged. When beta is 1, the entire sequence gets corrupted. In language, it's common to use a linear schedule, gradually increasing corruption over time. The next question is, how do we learn to go backwards from corrupted to well-formed text? Ideally, we would just flip the arrow of time by using the reverse conditional, where the past depends on the future. But of course, we don't know this conditional. The whole point of diffusion models is to learn it. But we can cheat a little bit. During training, we have access to x0, which is the original uncorrupted text. If we additionally condition on it, then we can get a closed-form expression that goes back in time. You can find the straightforward mathematical derivation in the D3PM paper, which I'll link in the video description. So this conditional, which we can calculate programmatically, can now act as a label for a model P with parameters theta, which aims to learn how to go back in time. So this becomes a standard supervised learning problem where we need to minimize the distance between two probability distributions. Various papers define various loss functions in terms of KL divergence, cross entropy, or evidence lower bound. To get a concrete understanding of how training and inference work in a text diffusion model, we'll look at LLaDA, which was published earlier this year. Here are the 3 stages in the model lifetime. pre-training, instruction fine-tuning, and sampling. During pre-training, we start with a general purpose piece of text, mask part of it, and then predict the masks. Interestingly, we randomly choose a single level of noise between 0 and 1. In this paper, they use the variable t for time, but what they actually mean is beta t for noise. They're basically conflating time with noise, which is a confusing but common practice in diffusion papers. Choosing a single level of noise makes training inefficient. Here, they're only predicting 2 out of 8 tokens, so the remaining 6 are an opportunity cost. In contrast, an auto-regressive model would have predicted all 8 tokens in a single training forward pass. This other paper shows that diffusion models require 16 times the amount of training compute to achieve the same validation loss. So ironically, diffusion leads to faster inference but slower training. This pre-training strategy might remind you of BERT, one of the very first LLM encoders. Similarly, BERT masked and predicted part of its input tokens. The difference was it only used a single fixed noise level, namely 15%. So in a way, BERT was a single-step diffusion model. Moving on to instruction fine-tuning, they're concatenating a prompt and the response. Crucially, it's only the response that gets its tokens masked and predicted. There's no reason to ever hide the prompt from the model. And finally, sampling proceeds in multiple iterations. The response is fully masked initially when the noise level is 1, and fully revealed at the end when the noise level is 0. Within one of the multiple intermediate steps, they start with a certain number of masks and then predict them. And here's the interesting bit. To prepare for the next step, LLaDA remasks a subset of the tokens. The reason is the model wouldn't know how to swap a regular token for another regular token. Remember, dog cannot turn into cat, only a mask can. And in order to avoid an infinite loop, they make sure to remask fewer tokens than in the previous iteration. So this is how LLaDA does training and inference. Of course, not all papers follow the exact same methodology, but this should give you a solid end-to-end intuition. And now the obvious question is, how well do text diffusion models work? It turns out they're starting to be competitive, especially for coding tasks where speed is critical. Mercury Coder, the diffusion model made by Inception Labs, performs on par with GPT-4o Mini at almost 10x the speed. Of course, this is by no means state-of-the-art yet, but it's usable. And remarkably, on fill-in-the-middle tasks, it outperforms similarly sized auto-regressive models by a significant margin. You can play with Mercury Coder in their official playground, or even call their newly released public API. Seed Diffusion from ByteDance also shows good performance on coding tasks. Not yet able to beat Qwen 2.5, but it's close enough. So that's how text diffusion works. For me, the biggest conceptual gap between image and text diffusion is the fact that in the world of images, models try to learn a local gradient of the landscape, the general direction towards real data. But in language, because it's discrete, there's no concept of a gradient, so instead we have to learn the landscape directly. Now, there's this one paper from Stanford which comes up with a proxy for a discrete gradient. They define it as the ratio between the probabilities of 2 neighboring spikes. It was very interesting, but this video was getting too long, so let me know in the comments if you'd like me to cover that in a separate video. The alternative would be video diffusion, which is also very interesting. Anyway, thanks for watching, and I'll see you next time.